Okay, let's talk about pressure of a fluid pushing on an object. So pressure of a fluid pushing on object. Okay, in this case I've drawn a tank of some fluid, and this fluid could be water, that's fine. I've got an object here, and I've only drawn a two-dimensional object, but really we think of this object as being in 3 dimensions. And then I've drawn this dotted line representing a column of water, if you think of it, just pushing down on the object. Okay? That's all this water, if you think of this as a bucket of water sitting on an object, we can envision that being a force pushing on the object. Well, let's see if we can figure out how much force is being exerted by this column of water on this object. Well, in order to do that, we need to figure out the weight of this column of water that's pushing on the object. All right, so now let's go through the steps of calculating that pressure. Now remember, this is a 3-dimensional box, so really this, I'm going to draw it here. This is really 3 dimensions. So we have the height of this column, or this rectangle of water pushing on the object, and then we would have a 3-dimensional, so we'd have a height that I've got here. We also would have a width and a length. So we have 3 dimensions of this column of water. Well, it's not a column, it's a rectangle the way I've drawn it. So something back here. So hopefully you can see the 3 dimensions of that, I've called it a column, but a rectangle of water that's pushing on this object. All right, so now let's see if we can calculate that weight that's pushing on the object. Okay, let's do that. So weight of a column of, I keep calling it a column, it's a rectangle, but it's just how I've always done this, I call it a column. The weight of the fluid being pushed on the object. Now, how do we calculate weight? Weight is mass times the acceleration due to the force of gravity, and so we know that as negative 9.8 meters per second squared. And remember, that's an acceleration due to the force of gravity. Force of gravity is pulling down on the objects and tends to cause all objects to accelerate with that rate. Mass of the object, in this case, is mass of the fluid. And we're going to use this formula to calculate that mass of the fluid. It's not important that you remember this formula. It's important to understand the concept that we're actually going through here. All right, so mass of the fluid is rho, okay? Rho, and I'll break that out here, R-O-H is what we say for that symbol. Rho is density of a fluid, and we've seen that before in the calculation of drag force equation. Rho is density of the fluid. V is the volume of the fluid, and so to calculate volume of the fluid, we would calculate the dimensions of the rectangle above our object that's in the water. Length times width times height. This would be the depth. This would be one dimension of the rectangle and the other dimension of the rectangle of the object. Alright, so that's volume, and then we just resubstitute some of these parameters in here. So now we have, therefore, the mass of the fluid is equal to rho, the density of the fluid, times A, and we can separate out A as being length times width times height. Okay, so rho, length times width times height. That's the mass of the fluid being pushed on the object that's submerged in the water. All right, so now let's look at the weight of the fluid. The weight of the fluid is now going to be, instead of just mg, it's going to be rho AHG, where this part right here is the mass of the fluid above the object that we're looking at. All right. Now let's just go back to our equation of pressure. Pressure is force over area. In this case, the force is the weight of the column, the rectangle of fluid that's pushing down on the object. Now I'm just going to substitute this W here for the force, and I get rho AHG. This is rho AHG, that's right here. And so this is weight of the fluid divided by area, and this is area of the force pushing on the object. So this would be the area of the object. So let's just bring that picture back up here. It'd be the area of the surface that this weight of water is pushing on. And that area is the same area as the dimensions of the column of fluid pushing on the object. So those A's are the same. All right, now, so let's carry that over to my next page of notes here. And we have pressure. I'm going to just rewrite the equation here. Rho AHG divided by A, and those A's are the same, so I cancel them out. So I'm left with this equation for pressure of the fluid pushing on the object is equal to the density of the fluid times the height of the rectangle above the object, and G, the acceleration due to the force of gravity. So let me write that out here. H really represents depth of water, depth of the object in the water. G is the acceleration due to the force of gravity. We already know this symbol, due to the force of, I'll just put G, and rho is the density of fluid. So if the fluid is more dense, it will be a bigger pressure. If the fluid is less dense, less pressure. Okay, so those are just those parameters defined. All right, so now let's think what pressure is in concept here. Pressure, and this is the important part, the pressure of the fluid pushing on the object is a function of H, or the depth of the object in the water. All right, this is the important part to know out of all this. The pressure of the fluid pushing on the object is a function of H, because rho is a constant, G is a constant. The only thing that's going to vary here is H, which is depth of the object in the water. Or another way of, another point of this that's really important when we start talking about buoyancy force is the pressure is pushing on the object from the fluid in all directions. So it's pushing in all directions on this object, all directions. Up, up, sideways, sideways, down, down, what have you. We're ultimately interested in the net pressure acting on the object, and ultimately the net force, and that's what we're going to be looking at when we start talking about buoyancy. Okay, so that's pressure of a fluid pushing on the object, and really this is a key point right here that we've got to pick up on this, and that's the equations to support that statement. Okay, thanks everybody.